Greetings and welcome to another test in statistics. Now, we've gone through what an ANOVA is, why you would use it, how exactly you go through and use it. And so what we're going to be covering next is taking those ANOVA results into a little bit more detail. Because after you've run an ANOVA test, it tells you that there is a difference. It's a difference somewhere going on that appears to be more extreme than likely to be caused by chance. But the problem is that the ANOVA test doesn't tell you where that difference is or what is causing it. It might be that all of the means are really different enough, or it might be only one is different, or one is different from another, or we don't know. And so what is done here is something that isn't always done. It's not always considered legit, but it is legit here, is running a post hoc test. Now, post hoc is, I believe, Latin for after the event. And in statistics, you're really not supposed to wait till after you gather your results and run a statistical test to then decide to run another statistical test. That's stacking the deck. That is basically result shopping, and it isn't a good thing to do. But in this case, it is, because what you can do at this point is run this post hoc test to tell you, if there is a significant difference, exactly what is causing it. And the one that your book talks about has one of my favorite names ever. It's called Tukey's Honestly Significant Difference, or HSD. So it's an honest post hoc test. I mean, granted, anybody could call themselves that, but it is. It's honest. It is legit to run, and it will basically tell you where the difference is. Because what it does is it compares all the possible pairs of sample means, okay, to look and see where the difference might be. So it compares sample group 1 with group 2 and group 2 with group 3 and group 1 with group 3 to see, or if you have more groups, it gets even more complicated than that. Now, I mentioned before the ANOVA that because of these complications with comparing group to group to group to group to group, that we don't generally want to do this because it can take a really long time. But the nice thing about Tukey's test is that if you have essentially run an ANOVA, you have all the data you need in order to run this. You don't need to run any more. You have one formula basically that you stick the information in that you got from the ANOVA, and it tells you whether or not the difference is significant. Now, in this case, there are two different formulas. One that you use when all the sample sizes are equal, and trust me, that doesn't get used very much because very often the sample sizes are not equal the way that they were in our example. But the formula when all sample sizes are equal is this. You take the mean of the first group, you subtract the mean from the second group, and you divide that by the square root of the mean squares within that you found during the ANOVA over n. And n being the number in each group. Okay? Since the number sizes are equal, all we need are n. And so you have all of those numbers if you ran an ANOVA. You have every single one of those numbers. And you just plug them in, and you find the difference between the two means, and you subtract them by some version of the standard error, which in this case is the mean square within divided by n, square root of that, and there's your Q. And we'll talk about what you do with the Q a little bit later. Spoiler. There's a table at the end of the book, just like there is with all the rest of these. Now, generally, however, when you run these, you're going to have sample sizes not being equal. And of course, when sample sizes are not equal, you have to take into account the different sample sizes. And this looks a lot scarier than it actually is. Yeah, it looks very much like the samples when they are evil, good Lisa, Freudian slip, equal. But notice the little tilde over the n, okay? Basically what we're talking about there with that little doohickey there is we're not just using n, we're not just using the number because the number is not equal, okay? The number is not equal. You've got different in each of these samples. So instead, we're using the n tilde which is equal to k, which remember is the number of groups, over 1 over n for each of the groups. So 1 over the n for group 1, plus 1 over the n for group 2, plus 1 over the n to group 3, plus 1 over the n to group 4, etc., going on as to how many groups that you have. Now notice that you add all of those together before you divide k by them. Don't do it individually. It'll also save you a lot of time. Okay? Now, that little n with the squiggle is called the harmonic mean sample size. I love the name. I tried to look up why it's called that, and quite frankly, I don't know. But apparently it's one of the Pythagorean means, so if you really want to know, ask Pythagoras. Except, of course, he's been dead for a very long time. You could probably ask a true mathematician. I'm not a true mathematician. I'm a psychologist who does statistics. So some of these things I have to admit on my own, I just kind of accept them, and this is one of them. So we use the n tilde for this. So using our prior non-significant example. Now normally if it's non-significant, you're not going to do this because it's not significant. Okay? But I'm going to do it because I want to show you how it is done. So let's pretend that we want to find out whether or not one of these is significant. So what do? Well, the first thing we need to do is find the one. I guess I was slightly incorrect when I said you didn't have to do any more math. You do have to find the harmonic mean. So finding that, you just take these and you plug the numbers in the way I show here. And what we find out for n tilde, or harmonic mean, n squiggle, is that is equal to 4.2857. Now that we have the harmonic mean, what we simply have to do then is plug the numbers into the formula. So first let's find the denominator, because it's easier to find the denominator. We only have to find that once, and we'll use it for all of them. Okay? Because it's the same n squiggle for all of them. So the denominator is 7.5 divided by 4.2857, which is the equivalent of the square root of 1.175, which is equal to 1.084, give or take. Once we have the harmonic mean, then you just plug numbers in. Groups 1 and 2, the difference between the means here. Now it's the absolute, those little lines on either side means that it's the absolute value, which means that plus or minus don't matter here. So what I always do is I just look at the two numbers and I subtract the larger from the smaller. They don't need to be in order. So I just subtract the larger from the smaller, and it helps me remember that, it's basically going to be the absolute value. So 17 minus 14 is 3. 3 divided by 1.084 is 2.7675. We do the same thing for the other comparisons, group 1 and 3. The difference is 2.5, so the Q is 2.3063. For groups 2 and 3, the difference is 0.5, so Q is 0.4613. So those are our Q values for each of those means compared to the other. Like I said, if you need to find the harmonic mean, after that, you just plug numbers in. You have all the rest of the numbers. So what we do now when we have these scores is we would go to the Q table, which I have also uploaded. It is under content. It's also in the back of your textbook. Now this Q table is a little bit different. They're all a little different. And part of the reason that I'm using these from your textbook is because your textbook tells you exactly what it is on the top or on the side. For Q, along the top, along the horizontal, the x-axis, we use K, which is the number of groups. And of course, the number of groups we have here is 3. You're not going to see a smaller number of group than 3 simply because if you only have 2 groups, you're going to do a t-test. You're not going to be doing an ANOVA. So we have the number of groups here. And then on the vertical, on the y-axis, we have the degree of freedom within, which you also know because you did the ANOVA. Okay, so you have all this data. So what you do then is you scroll down and you find, for instance, the number of groups is 3. So you go down to the degree of freedom. Okay? that we have, which happens, by the way, the degree of freedom within happens, remember, to be 10. So we go down here to 10. And since we're doing what we're doing, we're using 0.01, so we have 5.27. None of our scores are more extreme than 5.27, so yeah, we got nothing. But you knew that to begin with. However, if you look at the different Q scores, you notice that some of them are more extreme than others. And what you will often find then is one or two of them, maybe all of them, are extreme enough, are different enough from the others that they are more extreme than this, significant than this critical value. And it shows that indeed that is where the difference is. That is where the significant difference is at. So I believe that your textbook does an example that actually shows that there is a significant difference, unlike this one. But you just get the numbers, you compare it. Here we got nothing, none of them are significant, and that is essentially what you would say. Like I said, normally when you have a non-significant, you wouldn't run this simply because you don't need to know which is significant when none of them are. Although it also is sometimes interesting to run it and see whether or not a significance among one of them has been covered up by the others. That's a possibility. Can't hurt to run it. You pretty much have all the numbers except for the harmonic mean, and that's not too difficult to find. And with that, we're at the end of this chapter. Make sure that, remember, the homework is all of the questions from the end of the chapter. You need to do them and then send them to me the same way you send your test work so that I can give you credit for them.